Hello friends! In this video we're going to talk about the chain rule again, but we're going to talk about for a function of three variables, x, y, and z, where x, y, and z are all functions of t. So this is very similar to what we did in the video before this, where we did a function of two variables. The derivative of that function w with respect to t, partial of w with respect to x, times the derivative of x with respect to t, plus partial of w with respect to y times the derivative of y with respect to t, and then we add that third variable. So plus the partial of w with respect to z times the derivative of z with respect to t. So the dependency diagram, very similar. We just have three paths, three routes from w to t instead of two, but it's still the same. So let's do an example of what this would look like. For this example, we are going to find the derivative of w, a function of three variables, x, y, and z, with respect to t. Now, x, y, and z, those are each functions of t. So we're going to find that derivative, and then we're going to evaluate the derivative at t equals 0. So per the previous slide, we learned that definition, and the definition is going to require me to use the derivative of each of these intermediate functions with respect to t, and then also the partial of w with respect to each of these variables x, y, and z. So I'll start this problem by writing each of those derivatives first, since I know I'll need them. So dx dt, the derivative of x with respect to t, is the derivative of cosine, which is negative sine of t. The derivative of y with respect to t, the derivative of sine, is cosine t. And the derivative of z with respect to t is 1. So now I need the partial of w with respect to each of these variables. So the partial of w with respect to x, that means treat y and z as constants. So yx, that's just going to give us y. The derivative of that constant z would be 0. The partial with respect to y here, so that means x is a constant, z is a constant, that will be 0. This will be that coefficient constant, or x. And lastly, the partial of z, or the partial of w with respect to z, that means these guys are constants, so that's 0, and then the derivative of this variable z will be 1. So I can surmise that the derivative of w with respect to t is the partial of w with respect to x, y, times the derivative of x with respect to t, which is sine t, plus the partial with respect to y, which is x, times the dy dt, which is cosine t, plus partial with respect to z, which is 1, times the derivative of z with respect to t, which is also 1. So simplifying that, dw dt is negative y sine t plus x cosine t plus 1. And so we want everything with respect to that independent variable t, so I'm going to sub in what y and x were. Remember, y is sine t, x is cosine t. So I have negative, y was sine t, so I've got sine t times sine t, plus x was cosine t, so cosine t times cosine t plus 1, or dw dt is cosine squared t minus sine squared t plus 1. And hopefully we recognize that we have a double angle identity here. Cosine squared minus sine squared is cosine 2t plus 1. So there is my derivative. And we want to recall we were asked to evaluate the derivative at t equals 0. So dw dt at t equals 0, that's going to be a cosine of 2 times 0 plus 1. Cosine of 0 is positive 1, so 1 plus 1. That rate of change here is 2. So the calculation is easy, but what is it that we're finding? Well, remember, derivative is an instantaneous rate of change, right? So this 2 represents the instantaneous rate of change at the moment t equals 0. And this function here represents the derivative or that rate of change, and we can calculate it at any time t. So like a physical interpretation would say maybe this w function that we started with, right? So maybe this represented temperature, the temperature at each point in space at x, y, z on some curve with these parametric equations. Then the composite function, right, w of t, is not representing that temperature with respect to position, but now with respect to time. Or rather, it represents the temperature relative to t along the curve. So the derivative that we calculated, dw dt, is the instantaneous rate of change of some temperature due to the motion along the curve, right? So x, y, and z are describing the motion, and this is giving that rate of change at that specific time when we are at a specific point in space. So I hope that helps you understand how to find the derivative of a function of 3 variables, and those 3 variables are created by 3 different parametric equations. In the next video, we are going to talk a little bit about functions defined on surfaces, and so the chain rule for 2 independent variables and 3 intermediate variables. As always, email me if you have any questions.